today. It's 5 minutes later. I just hurt my foot. Okay, we're looking at 8.3, carrying out a chi-square test for goodness of fit. Remember, there are a couple of different kinds of chi-square tests we're going to be looking at. Goodness of fit is what we're looking at now. Homogeneity is what we're going to be looking at later. It's going to be a real party, guys, a real party. Okay, so we're going to do all 4 steps. All 4 steps. Do, state, plan, do, and conclude for chi-square in this lesson. Okay, a couple of things as we're going through this that you need to remember. Degrees of freedom are the number of categories minus 1, and our chi-square looks like this, chi-square, the sum of all the observed minus expected squared divided by expected, all those, add them all up. That gives you your test statistic. Remember that your p-value is found in a table or using technology, okay? We're gonna look at the table in this lesson, and then the next thing you do, which is either tomorrow if you stay on calendar, or like an hour from now if you're just working through all this 3 days before the test, will be on calculator, okay? So that you have the experience of both. And I'm not going to read through this because this is the same exact thing that it always says. We're going to create a null hypothesis that we're either trying to reject or not reject. We're going to compare our p-value to an alpha level or a significance level. And whatever our result is from our test is going to give statistical reasoning to support our conclusion, okay? Same thing that we've said over and over and over and over again in second semester. And we'll try not to sing to you guys. I'm sorry, that's so annoying. All right, here's our info from yesterday. Remember, ran down to Walgreens, got myself a bag of M&Ms. You know, now I'm thinking about this, I should have done like a reel of me going to Walgreens and buying the M&Ms and counting them. That would have been more entertaining. Anyway, in my bag, I had 21 red. No, I didn't. I had 21 brown, 37 yellow, 32 orange, 42 green, 51 blue, 27 red. And then I found the test statistic by subtracting, squaring, and divide by expecting, subtracting, squaring, and divide by expecting. And then I did that for all the colors and I got 9.25. And then we want to move forward with this test statistic, but first we need to prove a couple of things. We need to say, yes, this was random. I mean, if you consider my local Walgreens like a random sample. I mean, it feels like it is. It's like a random bag of M&Ms out of all the M&Ms. And it is definitely, and I didn't put this on here, but it is definitely less than 10% of all the M&Ms that exist. Definitely. And then this is the last thing, and y'all, I was super lazy. I said this, all expected counts are larger than 5. But if you put this on a test, I will not give you full credit. AP will not give you full credit. You need to show the math where you're finding all these expected counts. That was in the last video where we said, okay, there's supposed to be blank percent, that's brown, so 0.14% maybe, 0.14 times 210 M&Ms gives me the expected value of 27.3, and then do all of them and show that they're all greater than 5. Or your other option is to say, yellow has the smallest percentage. It was like 13%, I can't remember. And it's 29.4 because 0.13 times 210 is 29.4 or whatever it is, right? And therefore all the other ones have to also be larger than 5. I usually at this point when I'm doing my large counts test, I just go ahead and find all the expected values under this part because I'm going to need them later, just so you know, right? I just start with these conditions and grab my expected values from here. All right, here is, now remember, we're not doing normal curve anymore, so we've got this skewed curve. And we talked a lot about, is 9.5 big? Remember, big is bad, 0 is good, okay? So is 9.25 big enough that I can reject the null hypothesis? So let's say the alpha level is 0.05. Okay, well, look at this alpha level of 0.05. Now, if I get 0.025, that's less than 0.05, I can reject the null hypothesis, right? It's shockingly big. Guys, look at this. 5.02 is big. but only with 1 degree of freedom. If I have 3 degrees of freedom, 5 is fine. I'm not rejecting the null hypothesis. I'm accepting I'm accepting M&M's claim. So too big is determined not just by that chi-square test statistic, but also by how many categories there are, right? That how many categories there are really can make the numbers add up. Keep that in mind. Okay, so what do we need for the p-value? We obviously need a degrees of freedom. So how do we find a degree of freedom? What's n minus 1? N being the categories. So in this case, we've got 6 M&M colors minus 1. We've got 5 degrees of freedom. Okay, so we know we're going to be looking at this row right here of 5 degrees of freedom. Then we need to use the test statistic. So our chi-square test statistic is 9.25. So we go to that 5 and we go to 9.25, which is bigger than 9.24. So it's going to be like right here, right? So it's going to be like somewhere around 10%. So again, so we can go through that. Degrees of freedom was 5, so I'm only looking at that row. On that row, I find the number closest to our chi-square test statistic. What if it had been 9.23? Well, that's still bigger than 5%, and our 5% is our alpha level. What if it had been 11.08? Now we have an issue, right? Because it's less than the alpha level. So I use degrees of freedom, find my number, go up. That's going to give me my tail probability. That's going to give me my tail probability, which is what I'm going to use to compare it to the alpha level. So here's what it looks like, guys. State the hypotheses. We already did this. Plan. We're using chi-square goodness of fit test. Yes, you need the whole name because there's multiple chi-square tests. You need to say it's random. You need to say larger than 5. And I'm not sure why I left off the 10%, but I shouldn't have. And unique chi-square formula. This is on your formula sheet, which I should have shown you, but I didn't. I really failed making you guys this lesson. Then you do the math. Remember I said you can just show the first one and the last one and get your number, and that's going to get you from your table C your p-value. If you use your calculator, you have to show your function, defined variables, defined numbers, and so on and so forth, and then you can give the p-value, but you can't just say from calculator. You can say from table, but you can't say from calculator. I don't understand why, guys. It's crazy. AP craziness. And then to conclude, we say, assuming the claimed color distribution is true, so assuming the null hypothesis, there's a 10% chance of getting a chi-square of 9.25 purely by chance. And this is not statistically significant at the alpha level of 0.05. So we fail to reject the null hypothesis and cannot conclude the alternate, meaning M&Ms, they told us the truth. They were truth tellers this time. Okay? Take a second, pause the video, try the problem. Try the problem. Do it. Try it. It's going to be good for you. 3, 2, 1. Let's check your answers. Here we go. Distribution is the same. Distribution is not the same. We're using chi-square goodness of fit. Here's our conditions. Here's our chi-square. After getting our chi-square value of 29.92, we put it on the curve. Notice I did not draw a normal curve. I didn't draw this, y'all. I really borrowed it from the StatsMedic people. They did not draw a normal curve. They drew a skewed curve. We end up with a p-value from the table that's less than 5. Is a small number. Definitely less than 5%, right? Since the p-value is less than 0.05, we have convincing evidence against the null hypothesis, and we can conclude the distribution is not the same in Oro Valley as it is in North America. Number 2 says, if there is convincing evidence of a difference in the distribution of car color, perform a follow-up analysis. So it says the largest components of the chi-square test statistic come from other, which was 18 more than expected, and gray, which was 17 below expected. So then it's just, hey, look at this. I did this earlier with the dice problem where I said, I expect that it's heavy on number 2, right? So once you say, I don't think it's right, then say, go back and look at observed versus expected and say, here's where I think it's off. That is your analysis, your follow-up analysis is, okay, you drew an issue, there's a problem here, then state what the problem is. And you could go one step further if saying, which could lead to blah, 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 depending on what kind of data you're looking at. Okay. All right, guys, I'll see you on the flip side. Bye.